DVD, the technological leap that transformed home media from looking terrible to looking slightly less terrible. But for many of us, this minor revolution in resolution isn't the most memorable thing about the DVD era. It's this, the DVD Screensaver. I think anthropologists have long overlooked this facet of the human condition. Regardless of who you are, it is impossible not to get excited when this thing perfectly hits the corner. It's been referenced, it's been parodied, it's been memed, we all love it. Recently I started to wonder, is this actually guaranteed to happen? Does it depend on the screen size or aspect ratio? What about the shape of the logo or its angle of drift? Does it depend on where the logo starts on the screen? And if it happens once, is it guaranteed to happen again? So many questions that were bouncing around my mind like a DVD screensaver. And yes, I know this is a very silly question, but behind it lurks some fascinating mathematics, so come with me on this journey into DVD, where we will delve very deep to deftly visit divisibility, using this theory to draft versatile designs before devising valuable details, thereby determining valid discoveries. Enjoy. Most iterations of the DVD screensaver look like this. Some use a different logo, but the principle is the same. The logo moves at a constant speed and bounces such that the angle of incidence is equal to the angle of reflection. Hitting the corner means hitting two edges simultaneously. Our problem is this. Given a screen of arbitrary size and of arbitrary aspect ratio, and a logo of arbitrary shape traveling at an arbitrary speed at an arbitrary angle starting from an arbitrary position, will it hit the corner? If so, how many times? How often? That is a lot of arbitraries, but we can simplify the problem a lot before conducting our analysis, which will serve as a great introduction to number theory, divisibility, primality, Diophantine equations, and all that good stuff. If after this video you'd like to test your knowledge or learn more about these ideas, you should check out the sponsor of this video, Brilliant.org. I was in my first year of university when I first encountered the sort of mathematics we'll discuss later. As a youngster, I'd have leapt at the chance to learn it sooner, and it's all here at Brilliant. What's more, all the content is presented using these interactive modules, allowing you to experiment and gain an intuitive understanding. And once you're done with a lesson, you can progress through these bite-sized lessons at your own pace, with Brilliant tailoring the experience to meet you at your level. If number theory isn't what you need, Brilliant has you covered with lessons on mathematics from counting to calculus, and even has lessons covering other disciplines like computer science or physics. Whatever your needs, Brilliant is the best way to learn. So try everything Brilliant has to offer today for free for 1 month at brilliant.org/anotherroof, and the first 200 of you to sign up using my link will get 20% off their annual subscription. That's brilliant.org/anotherroof, or use code anotherroof at checkout. Thanks to Brilliant for supporting my channel. Back to this DVD problem, and let's talk about screens. A screen is just a grid of light called pixels. The size and aspect ratio can be simplified to how many pixels wide and tall our screen is. We will still assume the screen is a rectangle though, so apologies to smartwatches, dashboards, and those disgusting smartphones with the horrid bite taken out of them. Ugh. Because the extreme edges of the logo are the parts which make contact with the edges of the screen, we can idealize any logo as a rectangle. Now, motion on a screen isn't actually smooth. It's a series of static images played quickly to give the illusion of motion. These images are called frames. The speed of motion is essentially how many pixels are traversed between the frames. For example, as we just saw, 1 pixel per frame is quite slow, whereas 3 pixels per frame is much faster, and so on. Also, the angle of motion just comes down to how many pixels per frame the logo moves vertically versus horizontally. When these numbers are the same, it moves at 45 degrees. But say for example we move twice as many horizontal frames as vertical frames, then the logo will move at a shallower angle, actually about 27 degrees here. Now, I'm actually going to make a small assumption. It's necessary, and I think you'll agree that it's in the spirit of how DVD screensavers behave. The problem with arbitrary speeds and angles is that we might end up in situations like this. Say we're 2 pixels away from the edge and we're moving at 4 pixels per frame. Then on the next frame, we skip over the edge. I don't like this. It doesn't feel like we've actually collided with the edge. And God forbid we hit a corner in this manner. How unsatisfying is that? No, our assumption will be this. The only valid setups are those for which we see the exact frames the logo hits the edges. That's certainly how every screensaver I've seen behave, so I think this is justified. With that in mind, we can actually simplify things much further. there is a frame where the logo hits this right edge. Then we skip over a few pixels to the next frame, and so on. That means that these are the only valid horizontal positions. Similarly, the only valid vertical positions are these, and where these lines intersect, we have the only valid positions. For example, let's start with this 120 by 80 pixel screen and a 16 by 8 logo. Let's say the logo moves 8 pixels horizontally and vertically each frame. Well, then we only have these 14 valid horizontal positions and these 10 valid vertical positions. Therefore, we've reduced the problem from a grid of 9,600 pixels to a grid of 140 valid positions. No matter how it bounces, it must always exist in one of these places. This works even when the drift angle isn't 45 degrees. Let's say that each frame it moves 13 pixels horizontally and 6 pixels vertically. Now it only has 9 horizontal positions and 13 vertical positions, meaning the logo must always be in one of these 117 places. It's this new grid, the grid of valid positions, that we'll proceed to analyze. We don't even need to worry about the angle on this grid, since the logo always transitions to the next horizontal and next vertical position on each frame. If we warp this back to a square grid, we always move at 45 degrees. It's kind of amazing how every possible instance of screen size, logo size, drift speed, and angle collapses into the specific case of a point moving around a smaller grid, one square at a time at 45 degrees. The only thing we need to worry about is the starting position of the logo. So our problem is this: given an arbitrary starting position, will it hit the corner? Mathematicians have a name for this type of structure, by the way. A lattice. You can think of it as the usual Cartesian plane, but with just the coordinates of integer value. Specifically, this is a square lattice. Other lattices do exist, but the idea is always that we break a continuous space into a regular array of discrete points. Now, at this point, I'll say that I'm not the first person to analyze this problem. Milo of the channel ComputerCow has a great video on the topic, and he does it without making the assumption that I did and uses an entirely different approach in his solution. So if you're still curious about this problem after this video, you should go and check that one out. Let's proceed with this 13 by 9 example, and for the rest of the video, I'll assume that the width is greater than the height, as that more closely mimics a real screen, and if we were in a situation where the height was greater than the width, we could just rotate it without losing any generality. This point here, I'll give the coordinates 0, 0. Then we'll proceed with the usual x and y coordinates. If we start here at the point 5, 3, we see that the point kind of meanders around in this path and gets back to where it started without ever hitting a corner. Starting over here at 10, 2, however, we see that it hits these two corners. Why? It isn't obvious just by looking at the numbers. It's a 13 by 9 lattice. Why does 5, 3 fail while 10, 2 succeeds? And also, the pathing is unpredictable. Could you have predicted that starting from 5, 3, we'd eventually reach the point, I don't know, 0, 6? Could you have predicted that starting from 5, 3 but traveling in the other direction, we would hit the corner? I think what makes this difficult to analyze is the bouncing. Watch how the coordinates increase one at a time, but after we hit an edge, now one goes up while the other one goes down. And here they're both decreasing. This behavior makes it difficult to quickly picture the entire journey. So the next step is to reframe this problem without any bouncing. Here's the idea. Imagine the dot traveling up and right like this. Now we approach the top of the screen and usually we carry on going down. But what if we ignore this change in direction and just carry on going upwards? Now the dot is in this mirror world, a sort of parallel dimension. Before we get too excited, we should be super clear about what we're doing here and why. Notice now that the coordinates of the dot are increasing by 1 on both x and y components. Carrying on forever at time t, we can see that the coordinates of this square will be 5 plus t, 3 plus t, where t is the frame number, whereas in the bouncing model, it's much less obvious. Now, why is this a valid approach? Notice that the dot's journey in the mirror world is basically the same as in the starting screen. It doesn't matter that one is a reflection of the other. It will hit a corner in the mirror world if and only if it hits a corner on the original screen. And the same reasoning applies here when we hit this edge. Instead of bouncing, we'll just enter another mirror world, and another. When it hits a corner in one of these mirror worlds, it has hit a corner on our original screen. So we can reframe our problem. Instead of asking, when will the dot bouncing around the original screen hit a corner, we ask, when will the dot traveling in a straight line hit some corner? Now what we want to know are the coordinates of all of these corner spaces. Notice that the original screen has coordinates at 0, 0, 0, 8, 12, 0, and 12, 8. Now the next corners horizontally have x coordinate 24, and the next have 36. So we infer that the corners repeat themselves horizontally in increments of 12, and similarly increments of 8 vertically. That might be a bit counterintuitive because this is a 13 by 9 screen. So why aren't the corners repeating themselves in increments of 13? Well, you need to think about what you need to add to your position to get from one to the other. So for example, if you're here, say you're in position 1 horizontally, to get to position 13, you need to add 12 positions. So from 1 to 13, we add 12. Now, because these red lines actually form the boundary of both screens, if you're here, you're already in position 1 on this purple screen here, so you need to add 12 to get to the next corner. And similar reasoning for the vertical increments. I want to make this super clear as it's crucial for the rest of the video. A 13 by 9 screen will have corners at intervals of 12 and 8, and in general, an x by y screen has corners at intervals of x subtract 1 and y subtract 1. So what this means is that the coordinates of all the corners look like this: a multiple of 12, comma, a multiple of 8. We write this mathematically as 12k1, comma, 8k1, where k1 and k2 are integers. Now we've already said that starting at 5, 3, then on frame t, then the coordinates of this point are 5 plus t, comma, 3 plus t. So when does that equal 12k1, comma, 8k1? i.e. when does it hit a corner? We're essentially asking, when is there a value of t such that 5 plus t is a multiple of 12, while 3 plus t is a multiple of 8? Well, if 5 plus t equals 12k1 and 3 plus t equals 8k2, then after subtracting we eliminate t. The game now is to find k1 and k2 that satisfy that equation. And once we do that, we can substitute back into here to find t. The question is, how do we solve this equation here? Well, what makes this difficult is that k1 and k2 have to be integers. Otherwise, we could come up with any old solution like k1 equals 3 and k2 equals 17 on 4. But are there integer solutions? Well, it turns out not always. This one turns out to have no solutions, whereas an equation like 12k1 subtract 51k2 equals 21 does have solutions. How can we tell? And how can we find the solutions if they exist? And remember, we don't really care about these specific cases. We want to know in general when solutions exist. Essentially, for fixed integers x, y, and z, when is it the case that we can find integers k1 and k2 such that xk1 plus yk2 is equal to z? An equation which is constrained to the integers is called a Diophantine equation, and they are some of the most fiendish equations in mathematics. Simple on the surface, but sometimes requiring extraordinary depths of theory to solve. You're probably already aware of perhaps the most famous Diophantine equation, a to the nth plus b to the nth equals c to the nth, where n is greater than 2. If a, b, and c weren't constrained to the integers, it's trivial to show that infinitely many solutions exist. But insisting on integer solutions, that gives us Fermat's last theorem, which took 358 years for someone to prove that no solutions exist. Restriction to the integers makes things hard. By the way, that's 358 years after Pierre de Fermat wrote his infamous margin note about supposedly having a proof. And in which book's margin did he write this? It was a copy of Arithmetica by Diophantus of Alexandria, one of history's most important mathematicians, and it's after him that Diophantine equations are named. Anyway, fortunately for us, we are only interested in Diophantine equations of this form, and there is already a wealth of ancient theory that we can examine to figure out when exactly they are solvable. Learning how to solve them will give you a greater appreciation for divisibility, primality, and all that juicy number theory stuff. We need to start by discussing divisibility. Things like divisors, multiples, Euclidean division, greatest common divisors, and so forth. You might be familiar with these concepts, but even so, it won't hurt to stick around for some division revision, but it's your decision. Take an integer like 8. We say a number divides 8, or is a divisor of 8, if multiple copies can be taken to make 8. The word factor is also used. The number 3 isn't a divisor of 8 because multiple 3s fail to make 8. You either have too few or too many. I'll often use the phrase 4s fit inside 8, as I feel that gives an intuitive sense for what divisors are. We see that 2 fits inside 8 and 1 fits inside 8, so the divisors of 8 are 8, 4, 2, and 1. Doing the same thing for 12, we can see that has even more divisors. Now let's compare these lists of divisors. Divisors of both are called common divisors, the largest of which is called the greatest common divisor. So in this case, the greatest common divisor is 4, and it plays a very special role in Diophantine equations. Let me go back to the previous example to show you how. So earlier we were looking at 12k1 subtract 8k2 equals 2. Now I'm actually just going to rewrite this to make it look like the standard linear Diophantine equation. I'm going to change this to a plus. We can do that because k2 is an integer and it can be positive or negative, so the sign of its coefficient is arbitrary. For example, if negative 5 was a solution to the first, then positive 5 will be a solution to this one, and so on. Now, we just agreed that the greatest common divisor of 12 and 8 is 4, and now I claim that the left-hand side of this equation can only ever be a multiple of 4. Now that's because 12k1 is just 3k1 lots of 4, and 8k2 is just 2k2 lots of 4. So we have a bunch of 4s plus or minus a bunch of 4s. So this must equal a whole bunch of 4s. Or algebraically, we can factor out that 4 and see this is 4 times something, in other words, a multiple of 4. So this left-hand side is necessarily a multiple of 4. So if the right-hand side isn't a multiple of 4, the equation cannot be solved. That's why this equation here has no solutions. And remember, this equation emerged from this specific case of the DVD problem, which we saw never hit the corner. No solutions. Let's think more generally now. So if we have integers x, y, and z, and xk1 plus yk2 is equal to z, then what we've shown is that if z is not a multiple of the greatest common divisor of x and y, then no solutions exist, and that is summarized here. So that's when they can't be solved, but what about when they can? Well, back to this example, imagine if this number is any multiple of 4. Does it then have a solution? The answer turns out to be yes, but it's non-trivial to demonstrate. Let me make a claim, however, which will reduce the problem. Imagine if we found k1 and k2 such that 12k1 plus 8k2 is equal to 4 itself. If it's possible to do that, then we're actually done, because if this number here were any multiple of 4, say 4n, then I can obtain a solution by just multiplying through this one by n. So, do k1 and k2 exist such that 12k1 plus 8k2 is 4? You're probably shouting at the screen now saying, yes, obviously, for example, k1 is 1 and k2 is minus 1 and infinitely many others. But remember, we're not here to do this for 8, 12, and 4. We're here to do it in general. For example, consider 657 and 210. Their greatest common divisor is 3, and is it obvious that k1 and k2 exist such that 657k1 plus 210k2 is equal to 3? How do we find them? In general, we want to show that for any integers x and y, we can always find integers k1 and k2 such that xk1 plus yk2 is equal to the greatest common divisor of x and y. To prove this result, we need an awesome fact about division. Now, I really appreciate that you've stuck with me so far, because we're getting thick into the weeds of number theory here. So if you want to take a quick break, now would be a good time. Welcome back, and as a reminder, this is the result we wanted to prove. And to build your intuition, let's just look at a couple of examples. So consider 81 and 63, whose greatest common divisor is 9. It turns out if we take negative 3 lots of 81 and 4 lots of 63, they sum to 9. So in our case, the k1 would be the negative 3, and k2 would be 4. And just one more example, two of my favorite numbers, 216 and 60. They have a greatest common divisor of 12. Pause if you want to work it out, but it turns out that if you take 2 lots of 216 and subtract 7 lots of 60, you get 12. So that's the idea behind this result. You take two integers, and you can always scale them in such a way that they sum to their greatest common divisor. So how do we go about proving that we can always do this in general? Well, the trick is to find a pair of smaller numbers which have the same greatest common divisor as x and y, and solve the problem for those smaller numbers. After all, smaller numbers are easier to work with. So let me just write some of this up, and for the rest of this section, I'm going to let d be the greatest common divisor of x and y. So the idea is we find these easier numbers, a and b, with the same greatest common divisor of x and y, which I'm calling d, and we solve the problem for the easier numbers. And now imagine that I knew what a and b were in terms of x and y. then I could resubstitute, simplify it all, and I'd have my answer. Now don't worry if you're confused, this is just an overview of the process that we're about to conduct. So the question is, what are these magical A and B that firstly have the same greatest common divisor and secondly can be written in terms of X and Y? The answer turns out to be really quite satisfying. Just as an example, consider 12 and 44, whose greatest common divisor is 4. It isn't immediately obvious how we write 4 in terms of 12 and 44. But here's another pair that have the same greatest common divisor, 12 and 8. Now, as we've already seen, it's easy to solve the problem for 12 and 8. I just take one lot of 12 and subtract one lot of 8. So I can solve the number finding problem for 12 and 8. But this involves 12 and 8 as opposed to 12 and 44. But what if we could write 8 in terms of 12 and 44? Then we could substitute and we would have solved it for 12 and 44. Now you might think that this just kicks the can down the road, as now we have another problem in writing 8 in terms of 12 and 44. But 8 has a very natural relationship with 12 and 44. Can you spot it? Pause if you want to think about it, because I'm about to give away the answer. 8 is the remainder of 44 divided by 12. And the number theory magic that underpins this whole thing is the following fact. Whatever the greatest common divisor of 44 and 12, that's the same as the greatest common divisor of 12 and 8. It's pretty amazing when you first see it, but there's a very good reason why this is the case. I've just realized I've accidentally had this prop here the entire time. I'm going to use it now, but it shouldn't have been there earlier. I only put it here to make sure that it would fit in frame at this stage, so apologies for that. I guess you could call it foreshadowing, but really it's just laziness. Great story though. So consider our numbers x and y. X is this purple one here, y is this blue one, and imagine that they have some common divisor d. Well, what does it mean for d to be a divisor? It means that multiple copies of d fit inside x, and that multiple copies of d fit inside y. Now look what happens when I do x divided by y. That means we see how many y's go into x without overflowing, and then we have something left over which we call the remainder. But we know that d is a divisor of x. They fit inside this purple line down here, which means they must fit inside the remainder. Thus we conclude that d is a common divisor of y and r. Now this goes the other way as well. Let's suppose that we have some common divisor of y and r, so just a number that fits inside y and fits inside r. But because x can be built from multiple copies of y plus r, that means d must also fit inside x. So when a number starts out as a divisor of y and r, it is in fact a divisor of y and x. That essentially means the set of all divisors of x and y is the same as the set of all divisors of y and r. So whichever member is the biggest must be common to both sets, so they share the greatest common divisor. That is summarized here, and just a bit of housekeeping before we move on. This is probably the way that you first learned how to divide at school, but we mathematicians call this Euclidean division. And we don't usually write it like this. We usually say that x can be written as some amount of y plus a remainder. We use the letter Q for quotient, and now notice a couple of facts about r. It is allowed to be 0, because that would just mean that y is a divisor of x, and that can happen. But also notice that r must be less than y. Otherwise, we haven't really divided properly. When we divide, we see how many copies of y fit inside x without overflowing. If r was greater than y, well, that means that we should have fit another copy of y inside x and increase q. So r must be strictly less than y. That's going to be important for later. So let's just remind ourselves why that is useful for our problem up here. Dividing x by y, we obtain q remainder r, and y and r have the same greatest common divisor as x and y. So it's easier to solve our number finding problem for y and r. So imagine we found those two integers there. But now we automatically know r in terms of x and y. So we can substitute that into here, and thus we've solved the number finding problem for x and y. Now you might be thinking, great, but what if we can't solve the number finding problem for y and r? Well, then we can divide y by r and get another smaller pair of numbers, and we can keep going until we can solve it. And because each one is written in terms of the previous one, we can feed the numbers back in order to eventually write d in terms of x and y. So let me now call these q0 and r0. So if we need to, we can divide y by r0, which has its own quotient and remainder. And if we need to, we can keep going, dividing r0 by r1, which has its own quotient and remainder. The notation gets messy here, so don't worry if you're struggling to follow. We'll look at an example in a second that will bring it all together. Let me just reiterate why this works. X and y have some greatest common divisor, and this result here shows that this is the same as the greatest common divisor of y and r0. And that's true whenever we do a division. So the greatest common divisor of y and r0 must be the same as the greatest common divisor of r0 and r1, which must be the same as the greatest common divisor of r1 and r2, and so on. And the second thing to observe is that these remainders are getting strictly smaller each time. r0 must be less than y, r1 must be less than r0, r2 must be less than r1, and so on. So eventually, this process will terminate, because the remainder is always non-negative. So if they keep getting smaller and smaller, it must eventually terminate at 0. Okay, so the notation is a nightmare. Let's look at an example. Let's go back to 657 and 210. Their greatest common divisor is 3, and how do we express 3 in terms of these? Well, it's easy. You take 97 lots of 210 and remove 31 lots of 657. How do we know that? Well, following this process, if we do 657 divided by 210, that's 3 remainder 27. And now we repeat. 210 divided by 27 is 7 remainder 21. 27 divided by 21 is 1 remainder 6. 21 divided by 6 is 3 remainder 3. 6 divided by 3 is 2 with no remainder. Now it's no coincidence that the final non-zero remainder is 3, which is the greatest common divisor of 657 and 210. That will always be the case. Let me just quickly show you why that is. We'll actually do this in general, so we're endeavoring to prove that this Rn is the greatest common divisor of x and y. First observe that Rn fits inside Rn-1 perfectly. It's a divisor of Rn-1. It's a divisor of itself, and it's a divisor of Rn-1, therefore it is a divisor of Rn-2. If it's a divisor of both of these, then it's a divisor of the previous two remainders, and so on. So working all the way back up this chain, it must be a divisor of x and y. But why must it be the greatest? Well, pick any divisor of x and y. So it divides x and it divides y. That means it must be a divisor of y and r0, which means it must be a divisor of r0 and r1, and so on all the way down to here. Now our number now must be a divisor of Rn-1 and Rn. If it must be a divisor of Rn, that means that it's either less than Rn or it's equal to Rn. Sorry, I kind of ran out of space there, but now these two facts combine. If Rn is a common divisor of x and y, that means it's less than or equal to the greatest common divisor of x and y. But we've just shown that any divisor, including the greatest common divisor, must be less than or equal to Rn. So it must be the case that Rn is the greatest common divisor of x and y. Now this is great for our number finding problem because it means that this process will always yield an equation that involves the greatest common divisor. Now all we need to do is unpick all of these steps to write the greatest common divisor in terms of the original numbers. First, I'm going to rearrange all of these to make these remainders the subject of each equation. Now remember, we want 3 in terms of 657 and 210. We've currently got 3 in terms of 21 and 6, which we don't want. But we do have 6 in terms of 27 and 21 in terms of 210 and 27. So starting with this bottom equation, we can rewrite 6 as 27 subtract 1 of 21. And now if we expand and simplify this, we essentially have 4 21s subtract 3 27s. But now we can replace 21 with 210 subtract 7 of 27. Expanding and simplifying, we essentially have 4 210s subtract 28 subtract 3 lots of 27, so that's subtract 31 27. And finally, we can replace 27 with 657 subtract 3 lots of 210. So, expanding and simplifying this, we'll have 97 lots of 210 subtract 31 lots of 657. So we've done it. We've expressed 3 in terms of these two original numbers. We've essentially found the k1 and k2 such that k1 times 1 plus k2 times the other is equal to the greatest common divisor of these two numbers. Because these steps can always be unraveled in this way, eliminating all the intermediate remainders, this algorithm can always be used to find these coefficients k1 and k2, and that proves the result up here. This algorithm is one of the oldest known examples of an algorithm. It's called the Euclidean Algorithm, first documented by Euclid in his seminal work, Elements. The language used is different, but it's amazing to think that the mathematics here is absolutely ancient, well over 2,000 years old, and we're using it to solve some stupid DVD screensaver problem. We'll return to the screensaver in a moment, but first, this result is called Bezout's identity, in honor of French mathematician Etienne Bezout, who proved the result not just for numbers, but for polynomials as well. So let's bring this all together. Given a Diophantine equation of this form, let D be the greatest common divisor of x and y. We first argued that if z is not a multiple of d, then no solutions exist. But if z is a multiple of d, say dn, then by Bezout's identity, we can find integers such that x times the first plus y times the second is equal to d. Therefore, multiplying through by n, we obtain solutions for z. Thus, solutions exist if and only if z is a multiple of d. Now, I say solutions, plural, because it turns out that if one solution exists, then infinitely many solutions exist. The proof of that is beyond the scope of this video, so I put the details in an extended cut available to my patrons as a thank you for all of their support. Anyway, now we have all the tools we need, so let's bring this back into the land of the DVD screensaver. So we're going to go back to our lattice model and start with a lattice of width x plus 1 and height y plus 1. Why not just make it an x by y array? Well, because the algebra is easier this way. Remember, the corners appear in increments 1 less than the size of the array. Remember the 13 by 9 case, which had corners in increments of 12 and 8? Well, the coordinates of the corners in the general case will be at a multiple of x horizontally and a multiple of y vertically. In other words, xk1, yk2. And remember, these are the coordinates of the corners when we duplicate the lattice over and over again. So every multiple of x that way and every multiple of y that way. Okay, now let AB be the starting position of our point. Then, as we've already seen, A plus T, B plus T are the coordinates for the point at frame T. However, this is only if it starts by going in this direction. As we've sometimes seen, the direction matters as to whether we get a corner hit. So what if it starts by going this way? Well, now the x component is being reduced by 1 each time, and the y component is increasing by 1 each time, so the general coordinates will be a subtract t, b plus t at frame t. Also, quick side note, this direction, going down and left, is actually equivalent to this first direction going up and right, and similarly, down and right is equivalent to up and left. I'll go into the reasons for that a little bit later, but for now, trust me that these are the only two directions we need to worry about. I'll call this first one the positive direction, and the second one the negative direction. So we're asking for what value of t does a plus t, b plus t equal xk1, yk2? Or in the negative direction, we're asking what value of t is such that a subtract t, b plus t is equal to xk1, yk2. Now we go through the motions of equating components, and in the first case, we subtract to eliminate t, and in the second case, we add to eliminate t, thereby giving us a linear Diophantine equation in each case. And again, just like before, even though I've subtracted these, I've written them with a plus sign in the middle because k2 can be positive or negative, so this situation is equivalent. And now we have a pair of linear Diophantine equations, and we know exactly when they are solvable. The first one has solutions if this, a subtract b, the difference between the starting coordinates, is a multiple of the greatest common divisor of x and y. Whereas the second one, when we're traveling in the negative direction, has solutions when the sum of the starting coordinates is a multiple of the greatest common divisor of x and y. This agrees with what we've already seen. If you go back to our 13 by 9 example, here x is 12 and y is 8, the greatest common divisor is 4. We saw earlier that 5, 3 doesn't result in a corner hit. That's because it's traveling in the positive direction and the difference between the coordinates is 2, which isn't a multiple of 4. But if we start off going in the negative direction, the sum of the coordinates is 8, which is a multiple of 4, which does result in a corner hit. Similarly for when we started at 1, 5. Going in the positive direction works because the difference between the coordinates is a multiple of 4. Oh, it's so cool. I love that it actually turns out to be quite a simple rule, unlike some problems I've solved on this channel. Why not test your skill here? We have a 31 by 19 array, and we start at 1911. Which direction do we need to go in to guarantee a corner hit? Have you worked it out? Well, here x is 30 and y is 18. Their greatest common divisor is 6. These starting coordinates 19, 11 have a difference of 8 and a sum of 30. Only 30 is a multiple of 6, so we need to go in the negative direction. And that's exactly what we find. It works. And just for completeness, let me show you that it doesn't work if we start by going in the other direction. I made this spreadsheet so we can quickly see a map of all valid starting positions which eventually lead to a corner hit. Some of the patterns are really awesome. We can see that when the greatest common divisor is high, the number of valid starting positions is quite limited, whereas for a low greatest common divisor there are more valid positions. This goes all the way down to when the greatest common divisor is 1. In this case we say that x and y are co-prime, and here any starting position is valid. I also added a feature where you can see the path for a point starting in an arbitrary position to trace out its entire path. Again, some of the patterns are really cool, and here we can see that it seems as though if we hit a corner, we always hit exactly 2 corners. Why? And which 2 corners? And how long will pass between corner hits? Because sometimes it's a short path between them, and other times we journey through almost the entire screen. I thought these questions would have very complicated answers, but there's one last reframing which will give us very intuitive answers. First, let me convince you why, if we hit a corner, we always hit 2 corners. Now, the first thing to observe is that loops always form. This is because the entire path is determined by the starting position and starting direction. Reusing notation from before, there are only x plus 1 valid horizontal positions, y plus 1 valid vertical positions, and 4 valid directions. So this is the total number of states, and as soon as the frame number exceeds this, then we are guaranteed to revisit a state that we've previously been in, and that's guaranteed to happen if we let this thing run forever. Once we repeat a state, so position and direction, then we're guaranteed to just trace out the rest of the path, so it will just repeat itself. Okay, now suppose we start in this corner, and imagine what it would look like if we never hit a corner again. Well, since paths eventually repeat themselves, it must get stuck in a loop somewhere out here. So if you play this forever, it just gets caught in a loop without revisiting any corners. But this is impossible, because now if you play the tape backwards, we are saying that we are caught in a loop, and at some point the path just randomly deviates and hits this corner here. But once you're in a loop, you have to be in the loop forever, so this is a contradiction. We must visit a corner at another point. Also, play the tape backwards. What am I talking about? Play the DVD backwards. Okay, now assume that the only corner we visit is this starting one. But how can we get into that corner? It must mean that we are on the path that left the corner. But how do we get on that path? The only way to get on that path is to be on the path going in the other direction. In other words, the only way to get back to that corner is to completely turn around, staying on the same path but changing direction. The only way to do that is to hit a different corner. It's when we hit another corner that the path totally reverses, staying on the same path but reversing the direction. But notice that once we've hit that corner, we are going to repeat the exact same path and get back to the first corner. So this will just oscillate between those 2 corners, and that's why when we hit corners, we always hit exactly 2 of them. So if you keep playing this forever, it's going to oscillate between 2 corners, and that's really good news, because if you're sat around watching this screensaver and you miss the one time it happens, don't worry, it is guaranteed to happen again. But how long will you have to wait? What is the period of corner hits? And here, there's a really intuitive way to visualize it. Here we're going to go back to the duplicated mirror world model, and we'll start in 0, 0, draw the line at 45 degrees, and we'll time how long it takes to hit a corner again. So let's say this line keeps going until we hit a corner. But because we're traveling at 45 degrees, that at any point in time, we've traveled an equal horizontal and vertical distance. In particular, at the next corner, we've traveled a multiple of x horizontally and the multiple of y vertically. So the coordinates there must be a multiple of x and a multiple of y. And the first time that will happen will be at the lowest common multiple of x and y. For example, back to the 13 by 9 case, where x is 12 and y is 8, The lowest common multiple of those numbers is 24, so we predict that every 24 frames we will hit a corner, and that's exactly what we see. As for which corner we will hit next, we can work that out by considering the total number of horizontal and vertical journeys the dot takes. When we next hit a corner, we'll have traversed the entire width of the screen some number of times. If that number is odd, then we'll hit one of the far corners next, and similarly for vertical. If we've traversed the screen vertically an odd number of times, we'll hit one of the far vertical corners. Since we next hit a corner after travelling the lowest common multiple of x and y moves, dividing this by x gives the number of horizontal journeys, and dividing by y gives the number of vertical journeys. Finally, notice that once it hits this corner, it's going to retreat along this path until it gets back to where it starts. That implies that the period of the logo is 48 frames, twice the lowest common multiple. That's actually the case wherever the logo starts. If it starts in this position here, it won't hit a corner, but it will still have a period of 48. One way to see this is just to shift this line over. We see that this screen up here is basically a duplicate of this one, so its path from here will just repeat, and that corresponds to tracing out the same path around the screen. That's why these are the only two directions. The point eventually bumps into itself and starts the same journey as before, and travelling in the reverse direction is just doing the same path but backwards. Admittedly, I'm skipping a few details here, but to do it algebraically, it's quite muddy and technical, so if you want to see that, you can do so in the extended cut available to my patrons. Now, I thought we'd end the video by applying everything we've learned so far. Let's take this very classic looking DVD screensaver uploaded by Raul Blanco. It's 4K and 60 FPS, way higher quality than an actual DVD, but let's not split hairs. By meticulously counting the number of positions, we can see this logo has 317 valid horizontal and 186 valid vertical positions. So X is 316 and Y is 185. These numbers are co-prime, so wherever the logo starts on screen, it will eventually hit the corner. Now, their lowest common multiple is 58,460, so we predict that every 58,460 frames, it will hit the corner. At 60 frames per second, that's every 16 minutes, 14 seconds, and 20 frames. Luckily for us, this top comment tells us exactly when the corner hits are. I was about to say that this commenter has far too much time on their hands, but here I am at the end of a 45-minute video about DVD screensavers. The first corner hit is at exactly 13 minutes, 29 seconds, and 38 frames. We predict that the next corner hit will be at 29:43:58, and if we scan ahead and play, bang! There it is. So satisfying. Thank you so much for watching. This has been a video I've had in my head since last summer when I was at a party at a friend's house and he, for some reason, had a classic DVD player with the screensaver playing, and that got our minds spinning with questions. As always, a massive thank you to my patrons. Please consider supporting me if you enjoy my videos. Patrons get early access, extended cuts of select videos, we hang out on our dedicated Discord server, and much more. This has been another proof under another roof, and I hereby declare a victorious departure.